Hello friends, I'm sorry for submitting this review video so late, but here we go. I got it ready for you. If you already took your test, you can watch this and go back and correct your test after watching this review. Don't use your books, but you can watch this and go back and go, oh, this was that on your test, and fix it before you send it to me, okay? Okay, chapter what? I'm on page 543, chapter 8 review. I'm going to work the problem there, and then I'm also going to work the word problem there so that you can see how that goes. The example that you have on for 8.1, where we dealt with multiplication exponent properties, is 3y to the third all to the fourth power times y to the fifth equals what? And remember, we said when we have an exponent on the outside, we're going to times it, and we're also going to distribute it to every single term. So this becomes 3 to the fourth times y to the third all to the fourth times y to the fifth. 3 to the fourth, 81. You can do that. This just gets timed here, so this becomes y to the 12th times y to the fifth. Y and y, that is your first property over there. When we have the same base, we add the exponent, so this becomes 81. Y to the 12th plus 5, 17th. And we're done. We went from this big ugly thing to just a short answer, okay? So remember, always go by your properties, figure out which one is what, identify them, and they apply them. The word problem in your review part says the order of the magnitude of the mass of the Earth's atmospheres is 10 to the 18th kilograms. The order of magnitude of the mass of Earth's oceans, that's a lot of words, guys, is 10 to the third times greater. What is the magnitude mass of the Earth's oceans? 10 times greater means multiplication. So for that one, you're going to get 10 to the 8th times 10 to the 3rd, right? Same base. We copy the base. It's 8 plus 3, or 10 to the 11th. So times, that would mean multiplying. If you would have the whole mass is this, one of them is this much, how much of this in the first amount, then we divide. We did some problems like that. So that would be your 8.1. As we move on to 8.2, then we dealt with quotients. I yet again lost my eraser. You guys are used to this. I will have to find one, or my hands are going to be messed up. If I cross the page and I'm on 544, it says simplify x to the third over y, all of it to the fourth, okay? So we look, oh, never mind, times 2 over x to the fifth. So first of all, we're going to look at this. This looks like the distribution of the exponents of this fourth gets timed and distributed everywhere. This becomes x to the third all to the fourth over y all to the fourth times 2 over x to the fifth. We're going to continue to finish this one. This is the multiplication property. X to the 12th over y to the fourth times 2 over x to the fifth. We multiply fractions across, right? 2x to the 15th over y to the fourth x to the fifth. Is it a reason why I did it this way? Because normally x goes before y? Yes. Because I'm looking at this and I'm seeing that I have the same base right there with different exponents. So this becomes 2x to the 15th minus 5 all over y to the fourth, or 2x to the 10th over y to the fourth. X to the 15th divided by x to the 5th goes on the top, and it goes x to the 15th minus 5, right? This is my final answer. We also have a word problem here. Let me see if I can use anything else but my hand to erase what I need to erase. I cannot. Yes, I can. Okay, you are used with chaotic videos by now. Nothing new here. Let's look at the word problem, because that is a division problem. It's problem 24. It says the order of, oh, we're back on the magnitude, guys. The order of magnitude of the population of Montana was 10 to the 6th. 10, that's Montana. The order of magnitude of the total personal income for Montana was 10 to the 10th. 10 to the 10th. What was the order of magnitude of the mean personal income in Montana in 2003? To find the mean personal income, you're going to have the total income over the total population. The total income, 10 to the 10th. Total population, 10 to the 6th. Same base, which means I'm going to subtract the exponent, 10 minus 6, or 10 to the 4th would be the answer for 8.2. Okay? And 8.2 dealt with the quotient problems or rules. As we move to 10.3, oh, not 10, 8.3, I'm sorry, we talked about the rule where every number to the 0 power is 1. Okay, let me get this to focus on me. Hello. Here we go. And also that any number to a negative exponent will become its reciprocal to the positive exponent. So we're looking at the example in 8.3 that says 2x to the 0, y to the negative 5, and all of it to the 3rd power. There's 2 ways to do this. I'm lazy, you guys know this. So for me, this would disappear because any number to the 0 power is 1. I wouldn't even work it. I would be like, and it's gone. And now I get to distribute these three, sorry, not the tree, but the 3, everywhere else. 2 to the 3rd times y to the negative 5, all to the 3rd. This is the exponent of the exponent property, so we times it. 2 to the 3rd is 8. And then I end up with y to the negative 15th. Remember, I told you one of the very important rules of algebra is you cannot have a negative exponent. So this becomes 8 times 1 over y to the 15th. I need the reciprocal. And if you want to finish it, you can put 8 over 1 times it across. This becomes 8 over y to the 15th. However, if you just leave it for me like this, I would take this answer also. It is a correct answer. Okay? That's what we have over here. Let's look at a word problem, which is problem 29 in the review of 8.3. That says, use the fact that 1 femtogram, oh lordy, 1 whatever with an F, is 10 to the negative 18th of a kilogram, and 1 nanogram, 1 with an N, is 10 to the negative 12th. To complete the following statement, 1 N equals how many F's? So if 1 N is that much and 1 F is this much, how many of the, I can't say the word, that's my problem. How many of the femtograms are in 1 nanogram? Well, that would be 10 to the 12th, negative 12th divided by 10 to the negative 18th. Yeah, 1N equals this. Or 10 to the negative 12 minus 18y. Same base, different exponents, we subtract. Minus becomes a plus. This becomes 10 to the 6. 18 minus 12, 6. Okay? Okay. On 8.4, we dealt with scientific notations, and we kind of liked that chapter because it made it easier. Let's look at some examples. 2097, written in scientific notation. You lost me. I'm so glad I always turn around and look. I don't know why it doesn't focus, guys. I really am working on it. Here we go. We set the decimals in the back, and we need to have the first digit in between 0 and 10. So I got 1, that's 209, doesn't work. 20 is now between 0 and 10. 2 it is. This becomes 2.097 times 10 to the, and I count 1, 2, 3 to the 3rd, right? Let's try the next one, 0.00032. Again, my decimal is right here. I move this way until I get to one digit in between 0 and 10. 1, 2, 3, 4. 3 is in between 0 and 10, so this becomes 3.2 times 10. And because here we move to the left, that's a positive thing. We're moving to the right. I get 1, 2, 3, 4, negative fourth power because we move to the right, right? Let's see if we go the other way around. If we convert from scientific notation to regular number, I'm going to keep turning around to make sure this focuses. 4.3201 times 10 to the second. This little exponent tells you how many decimals you move over. I have to move it twice. 1, 2. So this becomes 432.01. And I moved it to the, oh, that scared me, to the left, to the right, sorry. And then the last one would be 2.068 times 10 to a negative power of that. Yes, it is -3. Here's my decimal. I need to move it to the left 3 movements. 1, 2, 3. This is where my decimal becomes point, and I have 2 empty ones. We said we're filling it out with zeros, and then 2, 0, 6. So conversion from standard form to scientific notation, and then from scientific notation to standard form. You got this. I have a lot of faith in you that you know how to work these, because it didn't really give you any trouble when we worked them in class. And that brings us to 8.5 and 8.6 that dealt with exponential growth functions. And you did like those, and we are using a calculator for those. If I would have to graph the function y equals 4 to the x, remember I told you I want 2 points, x, y. I just need you to do 0 and 1, and then we're using a calculator. Any number to the 0 power is 1. 4 to the first power is 4. And the reason I'm asking you to do this is because I want you to get those 2 points so you know when you curve. So for x is 0, y is 1. For x is 1, y is 4. And now you would go to your calculator, which I don't have here right now. You would go y equals, and then you would go 4, that little hat to the x, and then you're going to do zoom, and then you're going to do 6, right? And then you get your graph. And just remember, this is where you curve. That's why I'm making you do those points. Please don't draw a line through them. This is an exponential function. In this case, we have an exponential growth. And so it's going to be curved. It's not a line. It doesn't go through it. Now, they say identify domain and range, and you'll have this in your test. This is great because we said for the domain is always all real numbers on all of the exponentials. If it's growth or if it's decay, it doesn't matter. For my range, I said I'm always going to look, where are my y numbers? They're all over 0, which means y is greater than 0. If my graph, I'm just going to give you a crazy and say that this is where my 2 went, and you will go like this. If my graph looked like this, then I would have had, it doesn't touch 2, y is greater than 2, right? We look and go, what is the line that it doesn't, that my y doesn't touch, but it goes by it, and then I go, if it's on top, it's greater, and if it's on the bottom of that line, then it's less than. Okay, that's kind of what you're going to have to do here over and over and over again, except that's all you have to do. When we're going to move to 8.6, and we're probably going to use that income formula that is either for growth, that's the income, or for decay when we deal with cars and stuff that depreciates. I do not have, I'm not going to do a decay again here because you graph it the exact same way. It's just remember, for growth, okay, it's going to go up. For decay, it's coming down. That's how you know it's a decay. So if you look at the actual problems on 546, I'm going to go straight to 40 and 41. They say identify its growth of decay. Well, if it's a growth, it goes up. If it's a decay, it goes down. We are going to work problem 40 because I want you to remember how to do that. We just decided that is a growth, but we have 2 points. We have the points 0, 1, and then we have the point 1 and 4. And they say identify the function, the exponential function. Remember, we said the exponential is y equals a times b to the x. We're going to use our first point to find a. 1 equals a times b to the 0. B to the 0 is always 1. A is 1. We got A. Now we're going to use our second point to find B. For y, we're going to do 4 equals A, which is 1, times B to the first power. Well, B to the first power is B, times 1 is B. B is 4. So my function becomes y equals 1 times 4 to the x, or you cannot put 1 in there if you don't want to. Okay? Let's do 41 too, just to make sure that we know what we're doing. Okay? I'm going to erase this. Again, you have 2 points. You have 0, 3. And then you have 1, 1. And they say, first of all, we did say it's going down. So that's a decay. And now we want to know what is that function again. Y equals A times B to the x. We're going to use our first point to find A. 3 equals A times B to the 0. For y, we're going to use this y. For x, we're going to use the x of the first point. Any number to the 0 power is 1. Therefore, A is 3. We got that. We're going to use our second point, 1, 1, to find our B. So this becomes 1 equals 3 times B to the first power. B to the first power is always B. I need to solve for B, so that means I'm going to have to divide by 3. B equals 1/3. I now have both A and B, and I can substitute them in my original function. A is 3 times B, which is 1/3. All of it to the x. And now I have my function. I know that the sun is really reflecting, so let me do a little bit of a better job of you seeing what I did here. Okay. And then the last thing we're going to look is problem 42. That's a word problem, just to remind you how we use that wonderful formula. For exponential growth, we have A equals, let me write this correctly. Was it A or was it P? Let me make sure that we do it the way we did it every single time. I'm getting there. No, we always started with Y. And let me write it here because there's no glare. Y equals A. For growth, we had 1 plus R all to the T. A is initial amount. R is the growth rate. T is my time, most likely in years. Okay, this is for your exponential growth. For the decay, we have the similar formula, y equals A, but this time is 1 minus R all to the T, right? Also, we said that 1 plus R is your growth factor. In this case, we have A is the initial amount. R is the decay factor. Rate, sorry, not factor, rate. T, time in years. Which brings us to the last problem in review, problem 42, that says the value of a car is 13,000, which makes it the initial amount. Car depreciates or loses value at a rate at about 15% annually. Remember when I told you cars, the biggest thing that depreciates? 15%. We have to write this as a decimal, so it's 0.15. Find the approximate value. Well, first of all, write the exponential decay model, and then find the value in 4 years. So when we said when they want model, we don't mess with T and we don't mess with Y. Y becomes A, which my initial amount, 13,000, times 1 minus my rate, 0.15, all to the T. And we're going to finish it. This becomes 13,000 times 0.85 all to the T. This is my exponential model. Not model, but model. Okay? And now I want to know what is the value in 4 years. That T becomes 4. So this becomes Y equals 13,000 times 0.85 to the 4th power. You are going to put this in your calculator, and you're going to end up with about 6,700 and $86. So really, in 4 years, that car is half of its value, a little bit over half of its value. This is why I said, anytime you think of, this is one of the lessons that really applies to you every day. When you invest in something, think about how much is going to depreciate in time, especially when you're going to use a lot of money to get it. This is your review for chapter 8. I'm sorry that I'm submitting so late, but I hope it's going to help you a lot. Take your time to take your test. Make sure you know your rules and you have them close by. And then make sure I get your test before class tomorrow, at any point before class tomorrow, okay? Well, I love you guys, and I will see you tomorrow.